Hello Gophers and all those who are interested in Go. Today I am going to talk about how to concentrate on business logic by hiding transaction management and using a repository and unit of work pattern. Small piece of information. You can find the presentation using QR code at the bottom left of the slide. All QR code in the slides are links. Let's continue. I work at Avita, one of the most popular classifieds in the world. Our main language is Golang. We use it for more than 1,000 microservices. We use Golang almost everywhere, in cloud and network service, command line interface, DevOps, and web development. And we can handle about 300 million visits per month. That's cool, but we write the application with business logic, not a benchmark. My team and I work on smartphone reselling. That complex domain includes more than 20 states where a phone passes from a seller to a buyer through verification, repair, adding of warranty, and delivery. Nevertheless, I will use another domain as an example on the slide, the all-known domain of the shop. Unfortunately, we cannot directly use approach from other languages in Go because of the error handling. The small disclaimer, here is the most of the error handling in the slide is hidden. Instead of full error processing, I will hide if with checking from the slide. Then, Go is not conventionally object-oriented language. Go has unique insight into interfaces, no inheritance, no protected access modification, and others. Also, Go is a young programming language, and there are no ready libraries to build an enterprise application. Despite these reasons and the difference between Go and other languages, we can use some concepts from them. Let's see the repository pattern in Golang. The repository has a simple interface and hides saving, getting, and mapping data from the database that help us to concentrate on business domain instead of database. We don't add validation of usernames, product count in an order, or other business rules because the implementation of the concrete repository is not a part of the domain. The repository should work with only one model. If we add several models to the repository, we create a super repository which is difficult to modify, extend, and testing. The sequence diagram for any repository looks like that. When we call the repositories method, we convert data from the main view to database or vice versa. Then we receive or save data in the database. However, the repository can use data mapper pattern if we have a complex model, and the repository will work with a data mapper instead of direct calling the database. The description is simple, but what is inside? We little modify the repository interface to our model, and that's still simple. Then suppose we have a user with username, password, and other data, and each user have profile information about avatar, first and last names, etc. And that knowledge belongs to a user model. However, we store this data in database as two different tables. The repository includes machinery to hide the difference and help us think more about the domain, not the database. On the left side of the slide, you can see the main view of the model, and on the right side, you can see database view of the model. And you see that's different. And the repository help us to hide it. Let's see an example. This is getting model. I use SQLX to review the code of data mapping from a database when the app receives data. After receiving, we have a database view in the user row and profile row. Then we convert data in a domain view as a single model user with a nested profile model. In the save method, we convert the data view in the database and then save data. I use an insert and update in one query to place it in one slide. Then we use two tables, and we need to add transactions to prevent corrupting data if a problem happens in gap between two updates commands. Let's disclaimer. I simplify models to a few fields in the next slides to fit code on a slide. Now we have a user repository. Next, our business tells us to register a user. We create the method register, add validation method, and save a model with the registry. Then the product tells us that we must notify the new user about registration. For that purpose, we publish a message in queue about that. However, we can catch an issue when the queue goes down. We save data in the database and lose the message. This situation is unacceptable for us. Let's cover saving data and publishing with a transaction to prevent it. These are just two lines. The first one is to begin the transaction and the other one to commit. But we should explicitly pass the transaction to the repository and publish method. Passing the transaction in the repository complicates the code with additional knowledge. They say knowledge is power. However, in this case, additional knowledge is not about power. It's just complication for complication's sake. And we change our repository interface by adding knowledge about the database transaction. That makes our repository non-ideal, but we get atomic registration. It's not a big deal. We now have a registration, but the app cannot just create a user. Businesses want to sell goods, and we already matter and easy make a new repository with getting and saving methods. Then we create a new use case with validation, saving, and message publication in a transaction. And now we see our elegant solution with transaction registration and buying. While the developers are daydreaming, being perfectly content with the result of their work, business comes to them and demands a new scenario to increase the conversion of new users into our customers through purchase without completed registration. That is technique when users can buy things on the site without authorization and by just typing email or phone number only. Let's see on the slide. An attentive listener may have already noticed the issue in the code. The solution is the same as for the two previous scenarios. We add transaction control and pathing the transaction in the use cases. In addition, we complicate transaction control inside the use cases. The two lines are changed to if-else to decide whether the flow is on the top level or it was called something else, and it's not good. But as we know, with great business logic comes great legacy. Let me briefly recap what we have here. First, we have nested transaction use cases, and that's cool. However, the transactions spread everywhere. That forces us to duplicate the routine code to control them. Duplication adds an increased chance of making mistakes. Also, if we want to change the database, we must change the app in many places. Now I want to rephrase our issues to our wishes. The first one is an ideal repository for simple work with the database. Second, the use cases are transactional and nested. I want to save different models in the single scenario without thinking about how to open, close the transaction and roll back it on error. The third is supporting nested use cases. Now I want to rephrase our issues in our wishes. The first one is an ideal repository for simple work with the database. Second, the use cases are transactional and nested. I want to save different models in a single scenario without thinking about how to open, close a transaction, and roll back it on error. Also, I want to hide transaction control. And finally, I want to replace the database easily. We already have some wishes done as nested transactional use cases, but we need to get the others. Let's try to hide transaction control. The simple solution is using closure, but where should we place it? We can add closure in the repository. We call our scenario in the transaction, get the user and the order as a result, and then save them. However, I hoped that you will be skeptical about this solution. First, we still should pass transactions in the repository, in this case, in the order repository. Another problem is that for each new scenario, we need to code a new closure with new range of models. And the last problem is that over time, our scenario will become more complex and the user repository would be smarty and it would know about almost everywhere a model in the app. As a result, we would need much more time to extend and test our apps functionally. However, we can move the closer to a separate function and see the result. At first sight, this transaction is just a copy code from the use case. Take a look at transaction control paths in the closer and register scenario. Let's simplify our scenario with closure. We replace id lines on 2 and decrease the chance of create a bug. The code is entirely placed on the slide and looks better than it was, and I hope you agree with me. However, our code is still bound with the SQLX TX transaction. As a result, we can only change the database by rewriting all use cases, and somebody can make mistakes by handling control of a transaction. Next, I want to hide passing the transaction in the repository. To do that, we can use the factory method in the repository, which enriches our repository with the transaction. The factory method getting the transaction and save it in our repository, and then we can use the saved transaction in our methods. The code in the getting and save methods will change slightly. We replace one if condition on the single line. Nevertheless, I am eager to see how our use case would look after updates. We call this transaction repository method, and then the use case is not changed. Is that better than it was? Unfortunately, no. We add time dependency colon. We must call repository methods only after factory method, and I don't think it's cool. Could we use reflection in this case to remove the time dependency? Let's use a function with repositories as argument in this transaction. We pass it in our closer, then the reflection retrieves a list of repositories and calls the method with transaction to enrich them. As a result, we remove an argument with a transaction in repository method. However, a reflection is not a Golang way, and we still should pass the transaction in the use cases and the queue. Also, explicit passing spreads knowledge about the database through the application and where we can to store a transaction. Let's see how other languages solve this issue. In Python, the passing depends on a library. In SQL Alchemy, we pass the transaction explicitly as a function argument, and we already have it solution. In Django, transactions are stored in a global variable because Django processes one request in one thread. PHP uses the same approach because it does not have multi-threads processing at all. Unfortunately, this is not our solution at all. And fortunately, Go can work with multiple threads by Go routines. More enterprise languages such as Java or C# use thread local storage. That is similar to the global variable but limited by a single thread. But where to store a transaction in Go? Passing as an argument is not our solution. We want to hide a transaction to prevent high coupling use cases with a database. We have goroutine, and Go does not support built-in goroutine local storage. Could we create a similar solution by goroutine ID? And the answer is probably no. Golang does not allow us to get a goroutine ID directly. Go experts don't recommend using a goroutine because it contradicts Golang way, and they want to prevent building applications that associated all consumption with a single goroutine. And now we should use hacks to get an ID. Also, new language updates can break the hacks, and no one can guarantee the stability of the solution. However, some libraries implement goroutine local storage, but all of them are built on the hacks, and most are not maintained. Fortunately, we are not in 2016, and we have the context package that can be used to store the transaction. However, there are opinions that storing something more than primitive types in a context is a bad idea. That means, should we reinvent the wheel? Fortunately not. Some experts articles there is an exception for the specific values to be scoped to the request and destroyed after the request. That gives us the ability to use context to store a transaction inside the context. Excellent, we have a place for our transaction. Let's look at our closure. That's not so bad. We check a transaction in the context. If not, we create and put a new transaction in context. In the use case, we replace the transaction with a new context. Then we add getting a transaction from the context in the repository to work with the database. Also, we create a TR interface to replace direct database connection on a transaction and vice versa. Now we have a simple repository interface without the explicit transaction argument and nested transactional use cases. We can forget about transaction control by using with transaction closure. Additionally, we concentrate on working with database in closure and repository and can replace that database without changing use cases. However, we have a problem with closure, which is difficult to test because we cannot create a mock or stub for a function, and a global variable works with a database. Also, we need to rewrite use cases to add a new closure or replace the current one. Let's fix it. We must convert with transaction closure in a structure with an interface. The structure allows us to create a mock and pass the database as an argument instead of global variable. Let's name the interface manage. To do function calls do with settings with default settings, and do with settings control a transaction as a with transaction with additional features such as nested transaction, read-only transaction, timeout, etc. Then we introduce a general interface transaction which can commit, rollback, show the transaction status, and return an actual transaction. Also, we have the interface to create nested transactions if a database supports them. Also, we adding the settings interface stores standard configurations for different databases. We implement new settings for each database transaction because different databases have their configurations and abilities. We cast settings in specific interface to configuration the transaction in a factory. It's time to see what we have in the use case. Manager replaces with transaction and visually everything changes. However, we can mock manager or our stub for testing. In Java, we can hide the transaction from the use case by annotation or XML configuration. We can do the same in Go by reflection, code generation, some tricks with generic or just decorator. A simple decorator on the slide, but we should create a new decorator for each use case. It's not hard, but it's so boring. Let's try to use generic decorator. To get generic decorator, we should use trick. The trick consists of using the structure for arguments of the use case and naming the method identical in all use cases. In our case, we use the name handle. Then we create an interface which matches our use cases. The structure gives us the ability to create the generic interface which can work with any use cases. After that, we implement a decorator by using the interface and generics. The decorator is not ideal with generic, but we can easily implement it and remove routine code writing. The using of the decorator is simple and presented on the slide. Then we can simplify getting a transaction from the context in the repository. Let's create an interface to extract the transaction. The default method returns a transaction with the default context key, and thereby key returns a custom key. It is necessary when the repository processes two transactions simultaneously, but be careful with that. Also, when we create context manager, we set the default key to have the ability to change the key without changing code in the repository. However, we should cast transaction in the transaction structure of the database to work with it, and casting is not safe. We can create an interface for each database to skip casting in the repository. In the first iteration, the saving method looks like that. Let's use SQL Context Manager in the repository. This simplifies the code a bit and reduces the chance of error. Let me briefly recap what we have. We kept the transaction interface simple by hiding the transaction in the context. We get transaction operation nested use cases and hiding transaction by the transaction manager. And also we can migrate to another database without changing use cases. And finally, the solution does not create a problem with testing. But what did it cost? Fortunately, not everything. The solution works only on the Go 1.13 version, which was released in the 2019. It was not so long ago. Nevertheless, Go is updated by a minor version, and I hope you have already updated or it is not a problem for you. Also, there are a few ready transaction adaptations such as SQL, SQLX, Gorm, Mongo, and Redis. But you can write new adaptations by 70 code of lines. The next disadvantage is losing performance. The first benchmark shows that the difference with and without the solution is about 3.4%. The result was impressive, but the reason was SQL mock, the library for mocking SQL requests. SQL mock consumes a lot of resources. Therefore, I decided to rewrite the benchmark on SQLite in memory. The result was more natural, and the difference is about 18%. However, most applications which I have seen use database that store data on disk or are dedicated on another server. For that reason, I wrote a benchmark with MySQL on the same server. The file system has added overhead, and the solution takes the same amount of the time as code without the transaction manager. The network would consume significantly more time than the file systems, which mean the overhead of the solution would be minor. The other disadvantage is that we should pass context everywhere. I hope you already use context in applications to store request ID or other data for login or to cancel a request if a user closes a connection. Therefore, passing context is acceptable for you. The last and most considerable drawback is that we cannot do a long business transaction because the transaction in the database takes a connection and limited database resources. That can happen when we call external services serially. The simple solution is to request all data before the transaction, but we lose the ability to simply insert a use case into another. And another solution is the unit of work pattern, which I will discuss later. Now we can see and repeat the drawbacks. The first is a limitation of the Golang version when the solution can work. The next one is that there are only 5 adapters, but there are more than 5 database drivers and ORMs in Go. However, only 70 new lines can solve it. Third one, the solution consumes about 17% more than without it, or 5 microseconds. Next one is passing context everywhere. And finally, the solution does not support long business transactions, but the unit of work pattern can solve it. Let's take a look at what was and what is now in the code. We remove the storing connection of the database with the repository interface by hiding a transaction in context. In a repository, we replace checking an existing transaction with a context manager. Code is shorter than it was, and now it's harder for us to make mistakes. Then we can skip a massive block of database infrastructure to focus on a business actions in use case. The chart on the slide shows the dependence of the number of additional lines on the number of nested scenarios. The red line presents data without the solution. The green line is for the solution. The cross point is 1.8 when raw code loses in comparison to the solution regarding the amount of additional code in a use case. In addition, not only the count of code is growing when adding nested use cases, the chance of making bugs and cognitive load on developers is increasing too. Nevertheless, I give you a tool and you decide whether to use it or not. The link to the library is in the last slide. Now I want to go back to the long transaction drawback. I mentioned that the unit of work could solve it, the interface of the pattern for Golang on the slide. Let's describe each method. Register new marks a model as new. Register dirty marks a model as dirty or updated. Register clean marks a model as clean or getting from database without changes. And register delete marks a model as deleted. Then commit saves data atomically in a database in one transaction. And finally, rollback reset state to initial or previous success commit. Okay, we know what each method does, but how and when can we use it? Let's see the definition to catch it. Martin Fowler defines a pattern as maintaining a list of objects affected by a business transaction and coordinating the writing out of changes and the resolution of concurrency problems. The first fun fact about the definition, I mentioned concurrency problems, which are associated with the database, but they are resolved by pessimistic or optimistic lock, and it's not a part of the unit of work. The second one, in the original book Pattern of Enterprise Application Architecture, where the pattern was written, there is no rollback method. Let's understand what does pattern give us. First, that gives batch changes in the database, which can be significantly faster than sending each change individually. We can optimize insert by insert into values with multiple rows and other commands by removing network overhead on each command sending. Also, we can only update the changed data even if we change the model several times. The second, a business transaction can be long and not depend on the database transaction. And the last one, our update is atomic. What are disadvantages? First, we can't use a pessimistic log. Sorry, we can, but we lose the ability of a long business transaction because the optimistic log uses database transactions. Second is complexity. At the first view, the pattern interface is simple, but the implementation is not. Let's present the UML class diagram of the pattern. The first block is our pattern. The next block is the identity map pattern, which stores our models after they are registered in the sum state new, clean, dirty, or deleted. Further, we have classes to work with database transaction. I prefer to replace it with an interface to unchain from the database. The interface helps us to use the transaction manager, which we wrote. The next part of the pattern is mapper register, which returns a suitable data mapper for a model, and data mapper is a pattern which maps data from models to database view and vice versa. Some implementations of data mapper in other languages use reflection to work with any model, and they support configuration by YAML, XML, annotations, and etc. Additionally, if you want to implement the pattern, you should remember a problem with auto-increment identifiers. The application can get the identifiers only after the saving data in the database. You can use generic identifiers on the app side as a simple solution. We finish with depicting the UML class diagram. Next, let's see the example. Order and product are our models, and the pattern coordinates the saving of their changes. Order function is our business transaction. We check if the user exists in the external service, then we create a new order and mark it as new. After that, we get and mark the product as clean. Then we write off the product from our warehouse and mark it as dirty or updated. And finally, we commit changes to save it in the database. On the slide, you see the sequence diagram for our use case. We get mark change and save data. However, the most interesting part is hidden in the commit call because all magic happens there. When we call the commit, we create a database transaction, then we get the data mapper for a model in our use case. It is the order after that. The code execute batch changes in database. Finally, we commit the transaction. I hope I have explained the unit of work pattern and shown its complexity. Fortunately, we can simplify it to the interface on the slide. We remove identity map, mapper register, and data mapper patterns. The implementation still has a long business transaction and atomic update, but less is batch updates because we work with a callback function, and additionally, the model will be updated multiple times instead of once. That means if we add 3 commands updating the same model, we send 3 queries in a database. However, the original implementation optimized that. Nevertheless, the implementation even fits in 2 slides. We use callback function as commands, register methods, save commands in list. The command is a part of the data mapper, which we simplify. When our business transaction is finished, we call all commands in the comment method. Also, we can replace commands on queries or operations of some databases. So we return batch updates. Then we add the interface DB runner to send queries to a database as batch data. However, the model will still be updated multiple times instead of just once, and we have a problem with auto-increment identifiers. The next step is a complete unit of work pattern with blackjack and identity map, a fully implemented data mapper, and a mapper registry. Unfortunately, there is no ready library where we need to add only the data mapper for our model. However, the library with the name works tries to solve that problem for SQL databases. Also, you can help the Go community and implement the universal unit of work pattern. In conclusion, I want to remember what we have passed. The first is a repository. It is used if your application grows and the data in the application standing differs from the database view. Then we use the transaction manager to have nested transactional use cases and hide the knowledge about transaction in them. And finally, if you want a long business transaction, the unit of work is your solution. Thank you for your attention. The source code of examples and libraries accessed by second link. And please press the like button if the presentation was helpful for you, or write comments if I missed something, and simple writing of business logic. Good luck!